All right, this lesson will be on the law of the lever and mechanical advantage. It's the second lesson in the simple machine stuff. It's probably the longest, to be honest. The math is simple. Try and keep up. Take notes if you want to. And just remember there'll be an assessment on this stuff at the end. So when a lever is holding an object stationary, it's said to be in static equilibrium. The torques are balanced on each side. The sum of the load torques equals the sum of the effort torques. If we expand that, because torque equals force times distance, then you can say that the load force times the load distance equals the effort force times the effort distance. And then there's just a picture of a first-class lever. So then we've got these where we just have to determine the missing value. Now I'm only going to do two of them with you because we've skipped over the dynamics units where we convert masses into newtons, but that still gives me a chance to do these other two. So the missing value in the top left here is the effort force. So it's just going to be load force times load distance equals effort force times effort distance. So I'm just going to go 250 newtons times 3.7 meters equals the effort force times 1.5 meters. I'll be a little short on space here. I'll punch that in real quick. You go 250 times 3.7 divided by 1.5 equals, I get about 620 newtons of effort force on that first one. Now directing your attention to the bottom right. Again, it wants me to find the effort force. Same exact setup. It's load force, 120 newtons, times load distance, 1.5 meters, equals the effort force times the effort distance. Now, this is where some people mess up because the effort distance is not 1.5. The distances in machines are always measured to the fulcrum, to the pivot point. So that is 3 meters. So our effort force is equal to 60 newtons. The purpose of using any simple machine is to gain an advantage in force or distance / speed. And we can calculate that advantage by finding the AMA or the IMA. As a matter of fact, I'll skip over that. This formula, actually, let's just go to the next slide here. This formula here works for all machines. It's always the ratio of the load force over the effort force. So it'll just keep coming up every machine that we do. But since we know that load torque has to equal effort torque, and don't worry about that picture again, you could arrange it to say that it's also got to be equal to effort distance over load distance, and that's called IMA. And I'll talk just in a second about what AMA and IMA stand for. But in essence, a large effort distance will always result in a large mechanical advantage, which makes lifting easier, whereas a large load distance will result in a smaller mechanical advantage, which makes the work harder, but the load moves faster, like with a hockey stick. In a real machine, there's friction that takes away some of that advantage, and that's where we get our two types of mechanical advantage, the IMA and the AMA. IMA is just based on distances, so that's if there was no friction, that's the mechanical advantage you should get. But because there's actually friction, the actual mechanical advantage is what you will actually get. It's based on the forces involved. And the IMA is always larger than the AMA. IMA is always larger than AMA. Now, when we're solving a problem on paper, oftentimes they're just equal to each other, but you should never find that the AMA is larger than the IMA. That shouldn't happen. So let's solve a problem. A lever is used to lift a box with an effort force of 25 newtons. The box has a mass of 20 kilograms. Determine the actual mechanical advantage. I'm going to turn that load force, because I don't want to convert kilograms, into 200 newtons. Determine the actual mechanical advantage. And that way I have the same units for both. So we go actual mechanical advantage, load force over effort force, which is going to be load force is 200 newtons divided by 25 newtons, which is going to be 8. If we have a fishing pole like this and it says determine the ideal mechanical advantage, okay, so you go IMA is equal to the effort distance over your load distance. The effort distance is from the fulcrum to the effort force. And the load distance, again, watch the trick here. It's not real clear if the 120 is all the way to the fulcrum or not, but I'm going to say it's just to the effort force. So I'm going to say that load distance is 140 centimeters. And as you can probably already tell, it's going to give me a mechanical advantage less than 1. I got 0.14. Notice that there's no units on that because the centimeters will cancel each other out and just be left with 0.14. It's just a number. It's less than 1, so that means that it would be harder to move this load because we need more effort force because of those distances. But it would move faster and further. Let's try another one. What's the force needed to move the rock? We've got a 10-foot long 2x4 being used as a lever to move a rock. The rock has we're going to say it's a mass or a load force of 75 newtons instead of kilograms. If a fulcrum is placed 1 foot from the end, what's the minimum force needed to move the rock? So just to draw that out over here, the lever would be something like that. And you would be pushing with your effort force here, and the rock would be like there on the other side. So you have your load force here. It says the fulcrum's 1 foot from the end of the 2x4. So that would be right here, 1 foot here. It says that the 2x4 is 10 feet long. So that leaves us 9 feet over here. And that should help us go through this question. What's the force needed to move the rock? So we're solving for the effort force. So the load force being 75 newtons, FL times DL, 1 foot, is equal to FE, that's what we're trying to find, times the effort distance. So we go 75 times 1 divided by 9, 8.3 newtons is the answer. That's for part A. Part B says find the IMA. The IMA is equal to the effort distance over the load distance. The effort distance here was 9 feet. The load distance was 1 foot. And this one's real easy to do. It is just equal to 9. If there's a lot of friction, or if friction's not negligible, then your machine isn't very efficient. You can calculate the efficiency of the machine by going AMA over IMA times 100. And that about does it for the lever. I may post some practice questions to go with that, but ultimately you just need to go through this, go through the examples, make sure you can do what I did in preparation for a couple of test questions on that. All right, that's all for now.